Alrighty, cool. Yeah, thanks everyone for joining in. And welcome to the second edition now of the Byte Talks format that we have. And today we got Daniel with us. Actually, a long time contributor. He's involved in the Orbit project, right? He just did Fiatka. I saw him like on a couple of talks already, so he's really everywhere around it. And today he will talk about a topic called "From Hardware Design to Rich OS with No Code." Right. So let's see what he's up to. And yeah, Daniel, please go ahead. And everyone should be able to this time. Everyone should be able to formulate questions, unmute themselves. That should all work now. And yeah, thanks.
Great. So yeah, thank you very much for the brief intro, and hello everyone. So yeah, I'm Daniel. Yeah, as Christian just said, I'm all around the firmware space, and I've done quite some projects now. So yeah, over the time, I got a bunch of understanding of the whole space, and at some point, I started looking deeper and deeper and deeper. And well, eventually I figured, hey, let's actually also have a look at hardware design, because that is, sort of where we actually stem from. So yeah, with that, let me briefly show you what we're going to talk about today. I have, 4 very rough sections. In the first part, I will just talk about how we are currently getting to our so-called rich operating system. I'll also briefly elaborate on, what I mean by that. Then I will show you my actual day job world, which is web development. I will show you a bit, what we're doing in that space and how there might be a lot of similarities, actually. Then I will, talk a bit about hardware design from my current understanding so far. And then we will talk a bit about full stack design. And yeah, we will see about that. So yeah, just as a disclaimer, I will be talking about a lot of stuff I may not be proficient in, because I'm doing most of this here in my, spare time, just as a hobby. But yeah, I've done a lot of research. So yeah, we'll be happy if anyone would chime in at some point and, maybe broaden our perspective a bit more. So yeah, let's start with how we actually get to our rich operating system these days. And well, the answer is usually very, very simple. And I simplified this to a very short chain. And that is what, most people of you will have a very, very rough understanding of, like regardless of what exact projects we're talking about, or whatever hardware. So it sort of works like this, right? So we got our hardware. For the hardware, we write our firmware. We put a bootloader on top, and that launches our operating system. So that is very, very simple. And, at a very, very high level, it also looks like, you can pretty much do this like all the time. But, we keep producing more and more hardware, and it changes over time. So yeah, the thing is, then we also need to adjust all the other parts in our chain in a way. So yeah, the short answer really is firmware is what gets us to the operating system. And I mean, that's actually what we're talking about here in general, right? So this, after all, is the open source firmware foundation that is hosting this very talk. So yeah, and a big part of that, as I figured, is really, it sounds very weird and vague, but it's really about transitioning the hardware to a state so that an operating system can run. And that operating system can be anything. It can be a Linux, it can be a BSD system, Plan 9, or Windows, or Haiku, or, people have made many different operating systems over time. And those may actually have different expectation from your platform. So like the Linux kernel, for example, you can run it in a very simple manner. Just put it in memory somewhere, jump to that address in memory, and it will happily run. Very many cases at least. Some other systems, like BSDs, for example, I discovered, within one of our projects that is called Linux Boot, I discovered I can't just do that like with Linux. I actually need to do a bit more. And, that got me thinking, okay, well, maybe we need to, keep that simplification aside and actually look more into some details. But yeah, today I don't want to look into the details of operating systems and bootloaders, but actually the part before. And well, that is what some people also call bring up or platform initialization. or in more like in a more broader term, we can also call it firmware sometimes. So yeah, firmware can be a bit more than just platform initialization, right? So, but yeah, let's put that aside. Let's keep the general context here. So now here's my experience from working in the open source firmware space. And yeah, I will be a bit blunt with this now. So developing firmware, first of all, requires documentation, and we need tools. So those tools can be anything. On the documentation side, whatever we need is definitely processor manual. So if we are working with a processor, we would need to know how the processor actually works, right? So what happens when you power on the thing? Like when you supply power to it, what is the first thing it's doing or expecting, right? So it can be loading code from somewhere else. It can have its own internal storage and stuff like that. So yeah, there is a lot you would actually need to know. And of course, it doesn't really end there. When we work on actual mainboards, we also need the mainboards design. We would need the schematics usually and stuff like that. We may need debuggers, so they can be very helpful. There can be hardware components, software components, or the good old printf as the last resort always helps in a way. Then, of course, we need ports to connect to, like a UART. It can be USB port. With many modern SoCs I'm currently working with, there is actually an interface over USB that you can talk to. There are interfaces like JTAG or whatever sits on top of JTAG, which is usually a bit different per vendor or even per chip or something. We need the tool chains to build our code, and maybe other software utilities like what I just mentioned. When there is an interface over USB, we need a tool to talk to that USB interface, and more of that stuff. Now, the problem is some processors, they don't really come with full documentation. It might only be limited. On the other hand, we may get code on the other side. Sometimes it's only available in binary form. Sometimes it's actually source code. Sometimes you need to actually, change the code a bit or, make other adjustments, or maybe translate or port it to your framework so that you can make full use of that. So yeah, that's what we do eventually. We take that code and we build our frameworks around that. So there is like coreboot and oreboot, for example. Oreboot is just a fork of coreboot, to those who don't know. So essentially, we have this framework where we have the multiple steps of the chain that is defining the boot flow. And in a similar form, we also have that in the U-boot project. There is a similar concept in EDK2. And of course, there might be a lot more. Some even, sometimes vendor specific, which, we're maybe not talking about in the general sense. But, they may have their own solutions, but, still in a similar way. Now, how it starts when you get an SoC, like a system on a chip, a very simple SoC looks like this here. So there is a bus somehow that is connecting, the different components of the system. You have the CPU, the central processing unit. You have your RAM. It can be like SRAM, like static, random access memory. There is mostly like something like a ROM, that can also be in various shapes and forms. That would be the read-only memory. Sometimes it's called read-only memory, even though you can override it in a way, right? Like an EEPROM or, flash storage or whatever have you. And then you may have peripherals like UART, for example, which allows for, just printing out some characters or, full strings or, drawing ASCII art, whatever have you. So this is now what you're starting with. And as I said earlier, you would now need to know how this, SoC actually starts to work. So yeah, in very many scenarios, it just starts by firing up the CPU and it just, jumps to some address in memory that would be usually on the ROM. And then it would start executing code somehow. But yeah, that is, of course, an oversimplified view. Well, at some point comes your operating system, right? And now the thing is, your operating system will need drivers. And those drivers, well, they're very, very similar to what we do in firmware when we do our initial bring up. And well, so again, as a developer of an operating system, I will also need my documentation, I will need tooling, and it's very, very similar actually to what I would need as a firmware engineer. So we have a lot in common there. Now, the question I'm asking here is, well, can we actually generate that code that we would need? And, I've written down a few thoughts on that. So the first thing is, when we have an SoC design, and we're now talking about, some SoC or, hardware design language, that can be something like Verilog, VHDL, or, any other like fancier, more modern language or something. Technically, if we have that, we can also translate it in all other directions. From the design, we could generate a manual, right? So in the design, we sort of declared what the different blocks are, what the registers are, the semantics of, the certain bits in the registers and so on. And that is exactly what we would also find in a manual. So it's just a different shape and form. Now the question is, can we, do annotations in our SoC design where, we can write like human readable statements, like, design ideas and stuff like that, and then just generate the whole rest of the manual. In a similar fashion, there is a machine processable format that is called SVD, that is coming from the ARM space. There is a wider project called CMSIS. I'm not going into detail right now, but just roughly so you know where it comes from. And that gives you, well, essentially the same thing that a manual would give you or the SoC design would give you, just in an XML-based language. And then on the other side, for the operating system, we would declare all of that stuff that we have in these other three forms, just in a different language again, that would be called device tree. There's also other approaches, but I'm just sticking to this now as a simple example. There's actually people who have created tools to translate back and forth between some of those here. Somebody for the Orbit community, for example, created a tool that would take a manual from a chip vendor and then translate that into SVD. And now we can load that SVD into a viewer for SVD, which would be very similar to your PDF viewer that you would open the manual with, of course. But yeah, so the possibility is there. And from SVD, again, we can also generate other code, like, we can generate Rust code or C code. And, well, frankly, arguably also device trees. There is even a project that is actually taking device trees and from device trees creating SVD code. And from that, again, in turn, we can also generate other code again. So, yeah, I've added some references here if you want to look further into that. From the Rust embedded space, we have this very nice tool called SVD to Rust. So with that, we can just avoid writing a lot of duplicate. Essentially, it would be a duplicate, right? So it would be manual labor to translate from a manual to our code base, what could effectively just be generated. And frankly, we could eliminate errata with that, right? So if you have your SoC design and you write a manual for it, not by generating it, but really doing that from hand, you might actually make human errors just because we're humans and we're prone to doing that. And if you can avoid that in any of those translation steps, the better we might be off. So yeah, the idea would now be if we have any of those source forms and we know the model that our target operating system is operating with, then we can take our SoC design and directly translate that to whatever the driver would look like. Well, oversimplified at that point, it's just a theoretical thought for now. So yeah, we will see how far we can get in that direction. And with that, I want to make a very, very far jump now to a very high level thing I'm actually doing in my day job, which is web development. And on the web, we have a lot of very, very helpful and nice tools. And I'm now going to show you how I'm working with one of those. So I've made a tool that is called DTVis, the Device Tree Visualizer. It's one out of a few tools that allows you to load a device tree blob, and then you would get a visual representation of that. So you can navigate that. In this screenshot here, you can't really read very much of it. But what you can see is, there are these lines and there are these different boxes. So that is literally the representation of a tree as we know it from school, right? So when you draw a tree, you draw the nodes and you draw the edges between, and that effectively, declares a tree. So now the question is, while developing this here, can I use a very nice tool that would assist me in designing how I'm representing those nodes here? If you look at this, it's really just very, very bare bones by now. So it's not even developed that far. Originally, I actually suggested talking about that, but yeah, I've already presented that a few times in other places, and there is actually not much to talk about right now. But I will use this now as a simple example of how we work with components on the web. So there is a very nice tool that is called Storybook, and what I have here is something that visualizes one of the components that you saw in the device tree visualizer, which is one of the nodes. So this specific node here was just to represent a UART. So you would know in an SoC the UART would mostly be like memory mapped or something, right? So it would have a certain address, and that is exactly what the device tree visualizer is currently showing. So this here is a very, very simple box, which literally only has these 2 lines of information. Now, this tool here, Storybook, allows for doing the following. If you look at the bottom, you see that there is something called controls. And under controls, you see, there is a thing called data. And I can edit that data. So there is a button on the right-hand side. So I can put something else in there. Let's say I change it to I2C and I give it a different address. So, I can see how, this thing changes a bit by, giving it different input. Well, of course, conceptually, this is still a very similar thing, right? So we still have 2 lines of text and, they're not much different. So let's see what happens if we want to extend our component. So I will add a new property to our component. And that is now a blue dot. And well, this blue dot here, if you know how device tree works, this is now going to represent whether the component of the SoC is actually being enabled, or in device tree terms, okay for the system to use. So when your operating system starts and it parses a device tree, it will check which of the components in the device tree are actually marked as being okay. And only for those, the drivers would be attached then. Well, and the opposite of that would be disabled. So yeah, if I turn it off, well, in this nice tool called Storybook, you see down here, we have those radio buttons. So I will just click on disabled, and well, then I will get a red dot now. So yeah, this is literally what I have in my code. So in my code, I have something that just draws a blue or red dot. But yeah, so what I'm saying here is I have a very nice tool that helps me directly see what I'm doing. And so the question is, can we do something similar for hardware? So I have taken a look a bit at how hardware design works. And I must be honest here. So I don't really fully understand all of that, of course. So yeah, again, I'm a web developer, right? So again, another disclaimer. So I really don't know. I have no idea. I've never really done this myself, right? So what I've done so far is I have looked at a bunch of things. There is one term I kept seeing and hearing every now so often, that is hardware and software co-design. So that tells me that there are actually people that are aware of, having this large chain that I just described in the beginning, where you have your hardware on the one hand side and your operating system on the other side. They're aware of this whole thing actually making up a product, or a platform, or whatever you want to call it at that point. So yeah, let me now show you my perspective on this. So when I got into firmware, I already described to you, what it was a bit like for me. And now let's see, what my view on hardware design is. So I bought one of these very nice things here at some point. It's the Orange Crab FPGA board. You can also get it online. I put the link up here. And if you look at this board, it's like super tiny, right? So it's very nice for just carrying around and tinkering with it and so on. There's a few things on it, like there is a button down here, so you can press that button. There is an LED up here. There is another one, but I think it's only connected to this thing here for charge indication. You have this port here. If you know JTAG, well, you might recognize this. It's a very common shape of a JTAG port. Well, and you have a bunch more of these pins, right? So yeah, that was literally the first thing I did. And it's actually the only step I've taken so far. Well, frankly, because I haven't yet found the time for it. So what I did on this year, I ran a Blinky demo based on something called Amaranth. And Amaranth is a tool chain for developing hardware, and it's based on Python. So what this allows me to do is I can just say, hey, I have this board here, which is already supported by Amaranth. They have their support for a good handful of FPGAs and boards, and I can say, hey, let's see if I can light up this LED. So yeah, they have a small example project, and that is very much like when you get started with a programming language and you do your first step, right? Then you would do a hello world. So yeah, people who know hardware, they also know, hey, doing a Blinky demo is very much the hello world in hardware, right? So yeah, very nice thing to look into. So yeah, if you have kept track of the Open Source Firmware Conference, which already is 70, I don't know, 6th edition maybe this year. We've been around for a while now, and we have some good friends like Mulvad, for example. And out of Mulvad came another thing called Tilitis, and Tilitis is it's called a key, right? Like many things you can plug into your USB port. And what this here allows for doing is it's based on an FPGA, and you can load any code on that. But it's a bit different from just having like a microcontroller or something where you can also put your own code on. But in this case here, you could also change the hardware design, right? So you could put a RISC-V core on it, and that is actually what Tilitis provides already for you. But you could also change it and put something else on it. So it's really sort of what you make out of it. So if, for example, you want to implement some cryptographic features and you want to have that closer in your hardware so that you don't need to do as much in software, or maybe there are things which are not that sensible in software, you can actually implement that in hardware, or close enough to hardware using an FPGA. So yeah, it looks to me like FPGAs are really a very good potential prototyping platform if I were to develop something where I could say, hey, I have my design here, and now I want to generate everything up to my operating system. Technically, it sounds like a workable idea. So let's look a bit further. There is a framework that is called LightX, and LightX, they have this very nice ASCII art here. They already have a lot of different components. Like there is components for a DRAM controller, there is components for like PCI controller, all of that stuff, even SATA and video and Ethernet and what have you. So yeah, you can take those components. Now with those components, you can say, hey, this is what my SoC should now be. And with that SoC, you could now make up your board. So you could literally do this for, let's say, the Orange Crab board, for example, and also for the Tilitis key. So yeah, the FPGAs on those two boards are actually very much related. So yeah, this gives us, an opportunity to already leverage something, right? So I'm trying to push out some ideas here, but it doesn't necessarily mean that we actually need to invent things. So now the question is, how much can we design for reuse, right? So I've already talked about this idea of components, and there is already an existing ecosystem with the LightX framework and a bunch of others. So yeah, the approach is, very much what I know from my daily job from web development. We need this thing called components. And now the other thing I heard is, those components, if they can be declarative, right? Can we make a framework around that? So the LightX framework itself is object-oriented. And that is actually also true for the origins of what I work with on the web. Now the question is, does it fit well enough, or can we even bring it to a point where we can actually get to a very declarative approach and really say, hey, I want this SoC, it has to support these and these features. Now I get the SoC and I get the operating system, and that's it. And I can put my application on top of that. So yeah, that would really be the goal. Whether really that is feasible or not, is still up to some experimentation. Now, there is a wider ecosystem, of course. It's not just LightX. There is a website called opencores.org where you can find actually open cores for a bunch of different purposes. I haven't yet too much looked further into that, but I know that there is a good amount of course in there. Then there's a platform called design-reuse.com. It's mostly a media outlet, but they also have a database of reusable components for hardware, with full databases and so on. You would need to sign up and log into it. But yeah, that would allow you to browse that, catalog of components. And then, of course, if we look at GitHub, there is already a lot of open RISC-V cores there. I've even worked with, some SoCs which are based on open source cores that you can find on GitHub. So you can read their VHDL or Verilog language. I'm not sure. I think it was Verilog. Anyway, yeah, it's something we can definitely find, and also the peripherals, like the ones used by the LightX framework, they're actually also to be found on GitHub. So this slide is a bit garbled. Anyway, I will have an upload of the slides, and then you can still read the last part here. So what I've collected was, a bunch of changes in hardware design languages over time. And well, frankly, that started about more than 30 years ago already, where people put a lot of thought into hardware description languages. There's this one book from 1993, and that already included the idea of a declarative design. So yeah, the idea, as I said, is really you just declare what you want to have, and that would all then be generated. But still, here we are 30 years later. We're still not fully there yet, but I think we're getting somewhere. Just the next year, there was another, that is a paper on it. And also in the, you could say each decade after that, came a bunch more people with new ideas. Some are on IEEE, so on IEEE there is usually paywall, so I couldn't really look into that stuff. So it's not openly available, but you can at least read the abstracts and see what people might have been thinking. Well, and still in 2011, there was this idea of FPGA circuit synthesis, also in a declarative approach. So yeah, what you saw in LightX, they might have done something similar already, and that was at the university in Kansas. All right, so now in modern teaching, and this year is still based on 2013, but still used today, there is something that came out, also again declarative, and that was by Jonathan Bachrach and Krista Asanovich. And if you know that name, Krista was actually one of the people who started RISC-V. So yeah, who was also coming up with a language, especially for doing design of RISC-V. That language is called Chisel. The Chisel language isn't really mainstream yet. You can, read a bit more on Wikipedia. So I just took that small excerpt here as a citation. And it's saying that some developers may actually prefer Chisel. So I'm saying may because, don't take everything for granted here. It would require 5 times lesser code and would be much faster to develop than Verilog. That sounds very good, given that, Verilog has already been around for a very long while. And, if we can find something a bit more modern to, speed things up, the better we're off. So yeah, with that, I want to hop over to the idea of actually doing full stack design, which is also where I'm coming from in web development. So if you talk to web developers, they may sometimes say, hey, yeah, I'm working on the back end, or hey, I'm working on the front end. And you would rarely hear people say, yeah, I'm actually working on the interfaces in between, because, that is usually what you would need. And, where things may actually break apart. So it's always good to have a full understanding of the whole stack, right? And yeah, let's see how that might work in hardware. So yeah, again, let's look at declarative approaches with Chisel, right? So I will show you a very brief example. So the Chisel language, you can find that on chisellang.org, or on GitHub, it's now under Chips Alliance. It's based on the Scala language, which again is running on the Java runtime. So if you've never heard of Scala, never mind. So what you're going to see now is, something written in that language. But I think it should be mostly comprehensible. So yeah, if you just look at this here very briefly, this is describing an adder, right? So it's taking two inputs, it gives you one output, and that is an addition as we know it from school. So yeah, in this case here, it's a very, very simple thing. And well, it already describes the logic as we know it, right? It says io dot y, so y being the output here, is the sum of io dot a and io dot b, which were the two declared inputs. And that would be it. And now you already have a bit of hardware design in a very declarative language. I have no idea what this would look like in Verilog or VHDL or something. Yeah, but it actually looks like it's very, very workable to me. So yeah, what am I thinking? Or well, first let's see what other people are thinking about this, or what other thoughts they have pushed out so far. Because usually when you have an idea like what I wanted to talk about here, you do a lot of research and you figure, oh well, a bunch of other people already had those ideas. It's sort of the rule of the internet or the world, as we say, right? So just think of something, somebody else has already thought of it in a way. You can almost take that for granted. So yeah, people already said we would actually need for change in digital design. In this article or paper, they were mostly talking about power efficiency and stuff like that. And they were saying, hey, stop building very specific chip instances, start making generators for chips, right? So yeah, that is actually also what I've thought of, and also what other people have done so far. And actually, if you look in the RISC-V space, there is a bunch of these generators. I don't have a reference here now, but there is something I can refer you to, which is called Shakti. The Shakti project that is from India, they actually made generators for RISC-V cores and systems. So yeah, look into that if you're interested. Now, from a design thinking perspective, right? So we need to shift gears a bit again. So I said when we want to think full stack, we actually need to always have the full vertical stack in our view. So yeah, people also call that vertical design and integration. So my question here is, can we have something what I showed you in Storybook, but for hardware design? I assume such tools exist. I'm not sure. I haven't worked with those tools. They might actually be proprietary. So, we might actually want to have something open source for it. Now the question is, can we have peripheral designs and, also drivers, which are like components that I use on the web. So on the web, I have something that's called React. That is essentially a library that allows me to, design those components or, just declare them in a way. And I would assume that, we can build something very similar, or it already exists. So yeah, can we eventually have a single source of truth from the design, which leads to verification and production, and we have our full system? And well, can we actually bring this up to the full operating system? I've much recently looked into something that is called Zephyr. It's a real-time operating system. If you don't know it, just search for it. You will find a lot because it's actually wide in use already. It is declarative, right? So it is based on a device tree. So for your specific project, you would have a device tree and you would have configuration. And that creates your entire application that you would put usually on a microcontroller. Device tree itself is declarative. So when you declare what an SoC contains in your device tree, the operating system would then, need to have the drivers for it and just bind to those drivers, right? It's sort of simple. There are devils in the details, of course, but still, it is very simple from a high level. There is something called ACPI on the other side, which works a bit different. So in ACPI, instead of being fully declarative, you may also provide services which the operating system might need a runtime for and an interpreter. But yeah, that is just it's sort of different ownership or responsibility model, right? So some people say, yeah, I don't want to write drivers for everything in my operating system. Then you may say, okay, then you just use services provided by firmware. So but still, you could also generate the code for that. All right, I heard a ding sound. Is that somebody raising their hand? Oh, it's just a comment. Let me just quickly read that from the chat. Fun fact, most of these e-scooters, like Lime or Voy and so on, they actually all run on Zephyr. Yeah, little did I know. Yeah, interesting trivia. And I think there is actually also now a shift in Chromebooks, right? I think they also run their embedded controller based on Zephyr now. Yeah. Right. So, yeah, I kept searching, right? And I found something that is called Renode, which I hope you have also already heard of. And if not, I will give you a very brief description with a good slide full of bullet points. But definitely look into that because, the Renode project is actually trying to achieve a very similar thing. So, yeah, the website is just renode.io. And well, what you can do with Renode is you can design a full SoC up to a whole board. You can describe the peripherals in your SoC. You can already run co-simulation in Verilator. You can do verification with something called RISC-V DV. So when you have a RISC-V core, DV is like it's a bit sort of like a fuzzing tool or something. Yeah, have a closer look at that. I can't talk too much about it. It's already being used for testing Zephyr, for U-Boot, for TensorFlow. Even NutX just was recently added, I think, like almost 2 years ago. They have a very nice knowledge base that is called Renodepedia. So it's like the Wikipedia of Renode, with a very large collection of information. They created a hardware portal, which is a good collection of KiCad footprints and Blender models. So you can actually get a full 3D visualization of a board that you want that has certain components. So that is already very similar to what I'm doing with Storybook when I'm working on my web projects. They have a flow which allows you to generate a whole PCB visualization eventually. And their goal is actually to even generate everything that I just described, like beat code for Zephyr or U-Boot or Linux kernels or what have you. And if you want to know a bit more about it, Michael Gelda, one of the founders of Antmicro, has actually given a talk on that just like 1.5 or 2 years ago, on their vision of, just designing everything, just all at once. So yeah, that was sort of his title. So yeah, and with that, we're almost by the end. So I want to now introduce, well, what I've been doing over the years a bit. And that was the Platform System Interface project, which is essentially, a collection of design ideas. I'm trying to come up with specifications, noting down some ideas. I sometimes create a bunch of tools and, whatever have you, all around hardware, all around firmware, a bit on bootloaders, and even operating systems. And frankly, I want to get to a very nice user and also developer experience. A term that has been coined not too long ago, where the idea is that, you don't only want to provide something nice for, let's say, the end user of a product. Like, I don't know, me carrying a watch here, I look at the watch, I can do very fancy things with it. It should also be very nice to develop for those platforms. And that is frankly what I'm shooting for here. So you will find this on GitHub under platform-system-interface. And for essentially what I'm talking about here, I've also created an issue in the PSI spec project, where I'm trying to come up with, these specifications and so on. There's not too much in there, but there's a good bunch of issues with ideas. So you're very welcome to look into that. And if you, want to see slides of another talk I've given just like 2 years ago, that was at the Chaos Communication Congress when it was a remote edition. I've already talked a bit about, this whole stack or full stack thinking of, designing computers as platforms. And with that, I want to thank you very, very much for listening. And if you have any questions, well, feel free to ask them now. I already put the link down here to the site, so you can also download them from our website. And yeah, as promised, I will fix that one slide where it was a bit off. Thank you.
Thank you, Daniel, for the nice input here. I actually like the whole idea of composability. Let's say in hardware, and then drive that from a hardware perspective, kind of up through firmware into the operating system. That's quite neat. So I'm checking on Renode right now because I didn't knew that project, and I'm wondering. So I get like the whole composability about that, right? But sometimes we have like special things, right? So for example, when you do board designs, what always keep people busy, a lot of busy is like I don't know, DDR memory, let's say, right? Routing of the lines, right? No crosstalk and these kind of things, right? I'm wondering how, if you know by any chance, if there's any, validation for that as well, or is that they take like fixed components, or what's going on there?
Yeah. So honestly, I don't have a clue by now. But yeah, I mean, I very much do acknowledge. So when it comes to hardware, the game sort of changes a bit, and well, physics always get you, right? It's like people with the brightest ideas eventually had to mess with physics at some point.
Yes.
So yeah, it might be that is actually the harder problem to solve. Yeah, absolutely.
Yeah. Yeah, indeed. Yeah, curious. I gotta dig into that and see what's going on there.
Mhm.
And I think you mentioned like the SVD stuff, right? And that you can basically, or that there was someone. I think it's Danny, right? That you talked about. That was
Right.
yeah. Having like the specs or documentation from the SOC, transforming in SVD. Did you ever try that out in terms of generating code from that?
Mhm.
So I had a barely like a short look at SVD to Rust. Could you elaborate a little bit on like what is the exact output of when you punch in the SVD into, let's say, SVD to Rust?
Right. So yeah, let me briefly describe. First of all, what the Rust ecosystem has to offer. They have a concept of a HAL, like what we also know in other spaces, a hardware abstraction layer, and below that they have the concept of a so-called PAC, and PAC is for peripheral access crate. Already has peripheral in the word, right? And a crate in Rust is essentially what people otherwise know as like libraries or modules or whatever in your language. So the idea is that you generate the very low-level code, and that code is actually describing the actual hardware register. So like let's say I don't know, let's take a yard as an example. So that is usually a very simple thing, right? So yeah, I mean it's a bit modal and stuff, but you get the idea. It's just a handful of registers. We can still understand that. So like you might have yard at a given base address somewhere in memory, right? So what you could do is you could define a constant in your code for that base address. And on top of that, you could define like the offsets for the different registers. And then in your actual code, you would have the semantics of the registers, right? So you would do your, the weird bit shift operations and the ands and the ors, things that way can actually easily get wrong. And that is the idea of the pack crate. The pack crate would give you rich semantics on top of those registers. So instead of saying, I don't know, shift 1 by 5 and then or that to 1 shifted by 9 and then write that to the register at that address, what you would then do is you would actually say, hey, let's say the transmit register, you take the I don't know, okay, transmit is maybe a bit stupid, like where you just put a character in the buffer. It's it's much simpler, right? But let's say you're actually polling for the ready bit, right, which tells you the transfer is actually succeeded. So you would have register, which is giving you the status, and then you would say, hey, status register dot ready bit, while it's true or while it's not true, I'm not too sure at this point. Just keep looping, right? I mean, you might have your timeouts in between whatsoever, but yeah, the idea is that you would have semantics around those registers, and you don't need to manually fiddle with the bits here. So yeah, what that means is, well, you would eradicate a lot of human error in that regard, right? Yeah. So I mean, I'm not sure what the state is for you guys, but I've made so many mistakes by accidentally, I don't know, shifting wrong or doing an AND where I should have done an OR
Totally.
and stuff like that. It easily happens, right?
Totally.
Yeah. Mhm.
I can totally write perfectly fine code that totally fucks up, right? So I can do that in a very good manner. So
Yeah.
and I think that's true for everyone, right?
Yeah.
I mean, you still have like a human error in there, right? Whoever wrote the spec, they have to be right? Where you get the SVDs out and these kind of
Sure.
things.
I mean, in the end, it's turtles all the way down, right? So
Yes.
yeah.
But of course, I see that you have like a single source of truth, right? And then kind of go down from there. So that's pretty neat.
Yeah, exactly.
Yeah. Cool. Thanks. Yeah. No, that was really nice. Yeah, I like the whole concept. I totally think this is this should be possible in today's world. Let's say. Yeah. Maybe you can use LMMs for that or so. I don't know. Right.
Yeah.
All right. If no one got any questions, we would close it, right? And then I will see that I get the recordings up and running. And if people have any questions afterward, I think they are more than welcome to reach out to you. See the contact here.
Just one last reference. So if people would actually like to see the pack concept in practice, have a look at the Orbit project, where we already have a bunch of code that actually relies on a Rust pack. There are people who have written SVD files from the Rust community and then generated those packs for it. That is in the SoC space. If you look at microcontrollers, there is actually stuff that is already provided by the chip vendors. So, that is the ideal case, right? So where you can, rely on, hey, they actually know what they're writing there. If it is somebody who just copies something from a manual, you again have potential for error. So, yeah, have a look at that, definitely.
Yep. Orbit is for sure a project that you should look at no matter what, right? All right. Thanks, Daniel. Thanks everyone for joining in, and then see you next time.
Yeah. Thank you.